We are going to cover chapters 8 and 9 together in one shot. Chapter 8 is about memory management and chapter 9 is about virtual memory. So these are concepts very closely related. So that's why we're covering them together. So just for the background, remember that in order to run a program, you first create a process, and that process is created by bringing the binary code, the instructions of the program from the disk into the memory. And also some additional space is required for the stack, heap, and others. The main memory and the registers are the only places the CPU can access directly. The CPU, remember, cannot access read from or write to the disk directly. It has to go through the controllers. So while a program is running, all the instructions and the variables it needs should be either in the memory, or typically those values should be brought from the memory into the registers. Even if you want to read from a file, the CPU will communicate with the controller, and the contents of the file, at least the part that you're trying to read, will be read from the disk into the memory, and then the CPU will always read the data from the memory. So once again, the CPU is not able to read directly from the disk. It should ask for the content to be transferred first to the memory, then it will read from the memory. And the memory unit typically sees on the address bus the address of the data item to be read or written. So the memory unit communicates only through the address bus and the data bus. To read the data from the register, you need a single CPU cycle because it's already inside the CPU. It's just taken from the register into the ALU for the operation. However, when you try to read from the memory, even the memory is quite slow compared to the registers in the CPU. So trying to read from the memory requires many cycles and will typically cause a stall for several CPU cycles. So we have the cache that is between the memory and the registers. The cache is slower than the registers, but faster than the memory, but it's also larger than the register file, which is a set of registers. And when you're dealing with this, you should somehow make sure that the memory is properly protected because we might encounter some problems as we will be discussing in the following slides. So the CPU typically generates some address, what we call the logical address. We'll be discussing about this in a couple of slides. So the CPU generates the address of either an instruction or some data to be read or written. So the address that's getting out of the CPU should be sent to the memory unit. And remember, the memory unit is composed of multiple memory sims. Those are small boards that contain several chips on them that can store some finite amount of memory. So the address that's provided by the CPU, typically coming from the instruction, should be passed to the memory, which is composed of multiple sims, as I said. So that address selects the correct sim and also the correct set of flip-flops that store the bits. So we will call that a row typically in the memory. So the address is used for selecting the correct sim, the correct chip, and then the correct row in that chip for the data or instruction to be fetched, that means to be read or written. Now, when you're doing this, you should ensure that the address you're providing is correct. So when the address is generated from the CPU, it should be checked if it's correct. Now, there will be many processes that are running in the system simultaneously. So we should be able to differentiate between what we call the address space That means the set of legal addresses that could be accessed by that process. Typically, that means an address that is inside that process. We should make sure that a process is not reading from or writing to the address space of another process. So, for example, the process in the middle here should not be able to access the address of this process before or after. So to achieve that, we have two registers, the base register and the limit register. So the address that's generated from the CPU should be something between the value of the base, which is the starting address of the process, and base plus limit. So limit is this length. It actually shows the size of your process. So the address generated should be between base and base plus limit. So these are the first and the last addresses for that specific process. So when you're trying to run a program, you should bring the source, the binary code into the memory and execute. So typically there will be many processes. So these go through some input queue. Now, if you are considering a program, sorry, an operating system as simple as MS-DOS, in which you have always one program running, it's MS-DOS was not capable of running multiple programs together. In that case, the whole memory belongs to the process. So you can say my process always starts from this typical address. In the case of MS-DOS, it was leaving the first 256 bytes for the MS-DOS itself. So the addresses would be starting from 100 hexadecimal address, which would correspond to 256. So all programs always would be starting from the same place. That's why those were what's called the COM files. That means a program with the extension COM. So COM files always start from the same address. But that means if you want to have multiple processes in the system running at the same, almost of course at the same time, if you have a single CPU, you have to do scheduling, but at least with scheduling, you can have multiple programs running concurrently. So if you want concurrency enabled, then you cannot have multiple programs loaded into the same space. So in other words, the starting addresses of the processes should be different. Therefore, the addresses in your program, like your pointers, the address of your variables, that means the places in memory where your variables will reside, they should not be assuming that the program starts from a specific address, because when you run the program, you cannot be sure if that memory space will be available for you or not. So you should find a way of generating addresses that are what we call relocatable. So when you write a program in your source code, that means your program in C, Python, whatever programming language you're using, in your source code, the addresses are usually symbolic. That means you use symbolic names like A becomes 5. There, the variable A is actually a symbolic name, but of course, for the program, for the process to execute, you shouldn't have symbolic names like A, count, number of students, whatever, but instead you need the address of the variable where it resides. So the compiler takes your source code, which contains symbolic names, and compiles it into some binary code where you have relocatable addresses. So what the compiler does is it finds actually a binding between your symbolic names, variable names, function names, whatever, and their corresponding addresses. And these addresses are typically, as we said, relocatable addresses. That means rather than saying this variable is exactly at this memory location, instead you say this variable is, let's say, at byte number 14, starting from the beginning of this module, of this process or segment, as we will discuss later. So it is a relative address, relative to the beginning of that module. So if the module is shifted, that location, byte 14, should also be shifted accordingly. The linker or the loader will bind this relocatable address to absolute addresses. The absolute address is what we call the physical address. So that is the real address the memory management unit is expecting. Because as I said earlier, from the physical address, it is capable of finding the correct chip which contains that byte in the memory, and then the rest of the address is used for finding the correct row in that chip to find the specific address. So, for example, your compiled code could have a relocatable address like 14 bytes from the beginning of this module. But if the module starts as 74,000, then the absolute address, the physical address, would be 74,000 plus 14, therefore 74,014. And each binding, therefore, maps one address space to another from the relocatable addresses, or what we call the logical addresses, into the physical addresses. So when you write a program, all the variable names and function names, all the mnemonic names, in other words, should somehow be bound to some real physical addresses. So there are different stages of doing this. So at compile time, if we know the memory location a priori, that means when you write your program in the source programming language and you try to compile it, even while compiling, if the system knows exactly where the process will be located, then the compiler can create absolute code which contains absolute addresses. So it knows exactly where the program starts. Therefore, it also knows where the specific variables and functions, whatever, will be. Note that if you do something like this, and later you need to move the functions or variables around, you have to go back to the source code, make modifications, recompile, and then install the recompiled binary once again. Now, this may sound strange, and you might think this is never being done, but actually this is being done in, for example, embedded systems where you have very limited capacity. You want a very simple operating system. You want to do most of things in the firmware and the hardware. In that case, this is still being used, but not in your, for example, desktop computers and your phones, whatever, in most of the computer systems that you know. Another one is you can do this decision, you can make this decision at load time. So at compile time, you don't know where the program will be loaded. So the addresses you create are relative addresses. Therefore, you should be creating a relocatable code, because at load time, you should be able to load it wherever you have memory available. And the third one is at execution time. So not even at load time, at execution time. That means while the program is being run, so when you try to run the program, that's load time. But after it has been loaded, the instructions are being executed one at a time. Okay. When it is time to execute that specific instruction, if you're using execution time binding, the address is translated to a physical address or to a real absolute address only when that instruction is being executed, rather than when the program is being loaded into the memory. So when the program is being loaded into the memory, we're talking about load time binding. When we're talking about the binding being done while executing that specific instruction. We're talking about execution time binding. So this is showing the stages of programming and running a program. You write your code in source code. You compile if it's in a high-level programming language. If it's in assembly, then you use the assembler to produce some object code. Note that even in the case of assembly, you can use variable names, so mnemonic names. And the assembler, again, translates those mnemonic names to addresses. So you get the object code, but in the object module, you could be making use of some functions or even external variables from other modules. So those modules are brought together and linked by the linker, and you get a loadable module, which is taken by the loader when you try to run that program. The loader takes that loadable module and loads it into memory. But in that loadable module, you might be using some functions that are not actually defined inside your source code. For example, printf. Printf comes from some system library. So you don't have the source code of printf to be compiled. It has earlier been compiled and placed as a binary system library somewhere. Remember, printf, scanf, these functions are very frequently used. So rather than putting that piece of function implementation in every program over and over, we keep a single copy in what we call the system library. And only when you want to run the program, such very frequently used common functions are taken by the loader, only the ones that are used, are taken by the loader from the system library, merged together with the loadable module of the source code you have written, and an in-memory binary image of your process is created, and that's the one being run. And that could be working together with what we call the dynamically loaded system libraries. Now, these are what we call the static system libraries. And there are also dynamically loaded system libraries, as we will be discussing in a few slides. But those dynamically loaded system libraries contain functions that are not immediately loaded into the memory when you run the program, but instead they are loaded only when an instruction, actually only when you try to call that function. So until you call the function, although the process is running in the memory, until you call the function, the program is not yet the function is not yet loaded into the memory. So wrapping all these around, we have the logical addresses, also called the virtual addresses, and the physical addresses, which are the real addresses. The physical addresses are the ones that are seen by the memory unit. The memory management unit can work only with physical addresses. Remember, the memory management unit is managing the memory, which is composed of several SIMs. Those are small boards, the memory parts, memory units. The memory management unit uses the leftmost few bits of physical address to decide which one of those SIMs you're trying to make use of. The rest of the address tells which row in that SIM is the one that contains the byte or bytes, word, whatever, the data that you want to access or the instruction that you want to access. So the main memory unit, which is a hardware component, works directly with the physical addresses. Whereas in your programs, you cannot know, while writing the program, you cannot know where the operating system will place the process. So you don't know at the time of writing the program the physical address of the variables and functions that you're trying to make use of. Therefore, in your program, when it is compiled, you only have logical addresses. And while the program is running, the system needs to translate these logical addresses into the physical addresses. So if you're using compile time binding or load time binding, in both cases, there's no difference between a logical address and a physical address because in both cases, actually, what you have is the physical address. And you directly pass the physical address to the memory management unit. So you don't need a translation there. However, if you're using execution time binding, then you should be transforming the logical address to the physical address and send that physical address to the memory management unit. Now, the set of all logical addresses a process is allowed to access is called the logical address space of that process. And similarly, the set of all physical addresses a process is allowed to access is called the physical address space. So the memory management unit, which we've been talking about, is, in short, we will call that MMU. It's a hardware device that takes the virtual or logical address and translates it. Sorry, it's not the one that's doing the translation, but the logical address is translated to the physical address, and memory management unit is making use of that physical address. So if we consider a very simple scheme, we have a base register, as we discussed before. That's called also the relocation register. In the case of MS-DOS, there were 4 of them. And the user programs deals only with logical addresses. As I said, you don't know the physical addresses if you're using especially execution time binding. And that needs to be converted to physical address. So this is what we already discussed. Now, let me just remind the dynamic relocation. We also talked about this, but let me just remind it. So in the case of dynamic relocation, this is just to remind you that those are the functions that are coming from here, okay, from the dynamically loaded system library. So the routine, the function that you want to use is not installed, is not loaded into the memory until you make use of it. If the function is from a dynamically loaded or dynamically linked library. This provides us better memory space utilization because you don't use a memory space until you need that memory space, until you need to put the function there. So till that time, that memory space could be used for something else. Also, depending on the values of the variables, maybe the condition statements will not take you to the place where that function is being called. So maybe you're not going to call that function at all. For example, let's consider a function that handles some errors. If the error never occurs when you run the program in that invocation, if the error does not occur, then you don't need the error handling function. So why do you load it into the memory if you're not going to use it? That's the basic idea. So such routines are kept on the disk in some relocatable load format because we don't even know if we're going to load that function or not. So if it ever happens to be loaded, it needs to be loaded anywhere that you have some free space. Therefore, while writing the library, you don't know where the function will be loaded. Therefore, the function should be implemented in the relocatable format. And only when you try to access such a function, the operating system will find it in the dynamically linked library, it will get the address, which is a logical address. It will add that logical address, which is relative to the beginning of the module. It will add that relative address to the value of the relocation register. So if the relocation register contained 14,000 plus the relative address, which is 346, you get the physical address and you access server. If in another execution, the relocation register contained 20,000, then the physical address would be converted to 20,346 in such a case. Such working does not require special support from the operating system. It can be implemented through program design. Of course, you have special compilers that help you deal with that. And the operating system typically can help by providing some libraries which can be dynamically linked with your program.